All right, let's dive in. Today, we're going on a journey to find the absolute fundamental building blocks of mathematics. You could almost call them the atoms of algebra. We're going to start with a simple rule you probably learned in grade school, and by the end, we'll be touching on one of the biggest achievements in modern math. It's going to be a fun ride. You know, we all remember this, right? 2 times 3 is 6. 3 times 2 is also 6. The order just doesn't matter. It's comforting, it's predictable, it's a rule of the universe we can all rely on. But what if I told you that in the wild, fascinating world of abstract algebra, that comfortable rule often goes right out the window? You see, when mathematicians study something called groups, the order you combine things can be absolutely critical. Doing A, then B, can give you a totally different result than B, then A. It creates this kind of structured, beautiful chaos. So that's the big question, isn't it? How do you find order in a world where A times B isn't the same as B times A? Well, what if? What if inside all that chaos, there are these special, well-behaved little pockets that follow more predictable rules? And if we look at our source material, it points us right to the answer. The key is this idea of a subgroup, let's call it H, where H times X is the same as X times H. This describes a very special kind of subgroup, one that doesn't care which side you approach it from. And this special kind of subgroup has a name. It's called a normal subgroup. Now, I know that definition looks a little heavy, but the idea behind it is actually pretty straightforward. Think of the subgroup H as its own little club. A coset is basically what you get when you take every member of that club and mix them with some element X from the outside. A normal subgroup is one where it doesn't matter if you mix X in from the left side or the right side, you get the exact same result. It's perfectly symmetrical.
Okay, so that's one way to look at it. But you know how it is in math. There's almost always another angle, another way to test an idea that might be even more powerful. So is there a different way to figure out if a subgroup is normal?
You bet there is. Looking back at our source text, just below that first definition, there's a second one. And yeah, it looks a little more complex, a little more mathy, but trust me, this is an incredibly useful tool for testing if a subgroup is normal. So let's isolate this thing and really break it down. What this test says is, you take any element X from the big group and any element H from your subgroup, and you do this little combination, X times H times the inverse of X. The result has to land back inside the subgroup H. Okay, let's walk through that. First, just grab any element H you want from inside your subgroup. Second, you do this thing called conjugation, which is really just a fancy way of saying you sandwich your H between some X's from the bigger group and its inverse. And here's the magic part. No matter which X you pick from the entire group, the final answer you get has to be an element that's already inside H. It can't escape. So when you boil it all down, this test is all about stability. A normal subgroup is just so solid, so well structured, that it absorbs all these operations. You can mix it, you can shuffle it, you can mess with it using anything from the larger group, and it just stays perfectly intact, perfectly self-contained. So we've got a handle on what a normal subgroup is. But here's where it gets really interesting. It turns out they come in a couple of different flavors, and some are way more important than others for understanding the deep structure of a group. Here's the cool fact. Every single group that exists, no matter how simple or how mind-bogglingly complex, is absolutely guaranteed to have at least 2 normal subgroups. We call these the improper or trivial ones, mostly because, well, they're always there. They're not that special. And here they are. First, the entire group itself is always considered a normal subgroup of itself. Kind of makes sense, right? Second, the tiniest possible subgroup, the one that just has the identity element E in it, the element that does nothing, is also always normal. These are the 2 universal, but let's be honest, kind of boring examples. And that sets up a really important distinction, the idea of a proper normal subgroup. A proper one is just any normal subgroup that isn't one of those 2 trivial ones we just talked about. These are the interesting ones. These are the ones that actually tell you something unique and deep about a group's internal machinery. Okay, so proper, improper. Trivial, interesting. Why have we been digging into all this detail? Why does any of this matter? Well, this is the payoff. This is the big reveal. This simple distinction is the key to discovering the actual atoms of algebra. Just think about that for a second. If proper normal subgroups are the interesting, non-trivial building blocks inside a group, what would it mean if a group was so fundamental, so tightly woven, that it had none of them? What if it only had those two trivial ones that every group has to have? And that, right there, is the definition of a simple group. A group gets to be called simple if and only if it has no proper normal subgroups. It means there are no internal fault lines. It means you cannot break it down into smaller pieces using this method. It's indivisible. This is exactly why we call them the atoms of group theory. It's the perfect analogy. Just like every molecule you can imagine is built from the elements on the periodic table, every finite group can be built up from these simple groups. They are the absolute rock-bottom fundamental components of algebraic structure. So where do we find these atomic groups? How can we spot them in the wild? Well, the answer, believe it or not, comes from something we all learned about in school: prime numbers. It all has to do with the order, or simply the size of a group. And here it is, the big finale, straight from our source. Every group of prime order is simple. I mean, how elegant is that? It's this beautiful, powerful result. If you have a group and the number of things in that group is a prime number, like 3 or 5 or 7 or 23, you know for an absolute fact that it is a simple group. It's one of those mathematical atoms. So we'll leave you with this to chew on. If these simple groups are like a periodic table for mathematics, what kind of incredible, complex, and beautiful structures can you build with them? It turns out, finding and classifying all of them was one of the single largest collaborative projects in the history of math. And it all starts right here, with this simple idea of a group that just can't be broken down any further.